be there first before I could stack anything on top of it, right? And so forth as we move up the section, up the stack of rocks. So we can look at these relationships about what had to be there before the second thing could happen, before the third thing could happen, and we can kind of figure it out. For instance, let's look here. I've got these layers of rock here. Here's a sandstone. I can follow along. Comes along here. Oops, jumps up there. Ooh, goes down there. Well, I know that sandstone was kind of one flat unit originally, right? And let's see, I've got a batholith. This is a big intrusion of molten rock that comes up. And you can see how this has been faulted. The rock has been broken. This block has gone up. This block has gone down. Then this batholith has come in and it's obliterated the fault. And then I had another intrusion that came across, cut through the batholith, cut through the fault, and squirted in some intrusive here. So for that to be intrusive, I know this unit had to already have been deposited. This fault had to occur before this unit was deposited because it ends right there. It doesn't cut through that unit. This dike here, this intrusion of magma, cuts all the way to the surface. It cuts all of these units up here, which this one doesn't cut. So this dike had to occur last, much later than this, because it goes all the way through. So just looking at these cross-cutting relationships, what cuts the other thing? What's, 1, 2, 3, 4, 5 events? I can put them in order, and that starts building my package in my geologic timescale. Okay, here are a couple of examples. Here's a fault. You can see where the rock is broken. You can see this package right here is this package right here. So this fault has dropped this block down, this block's gone up, and this used to be hooked on right there. It used to be originally horizontal over a big lateral distance. So we can see that cross-cut. Here we see actually a magmatic intrusion. You can see this was all flat-lying rock, and now this dike has cut through that flat-lying rock as the second episode in that picture. Here's a close-up of a fault zone. You can see our flat-lying rock here, and notice we've got little chunks of it all busted up, all re-cemented here in the fault zone. So this kind of illustrates what we call inclusions. The second event includes pieces in it of the first event. So I know I've got to have, the flat-lying rock there first for pieces of it to be incorporated into the cement that filled the fault. So those inclusions help you really kind of put things in order. Okay, here's a clicker question. So get out your clickers and turn them on. Now you'll notice our little logo thing up here, and that's going to change when I turn the slide on. It'll start counting up from 0, and then the number on the very right of the box will start increasing as you guys click in. It'll tell who has clicked, how many people have clicked in to answer the question. We're going to let the thing run for 20 seconds. That's how long you have to answer it. I think you'll find that's really enough time. You can change your answer anytime. Hit your button that you want and submit it. And your questions, of course, are A, B, C, D, E. A is used for true, B is used for false in true and false questions. It's not labeled that way in your clicker, but that's how it works. Okay? So, the law of superposition states what? The oldest rocks are on top, the youngest rocks are on top, the oldest rocks are in the middle of the basin, the youngest rocks are in the middle of the basin, the oldest rocks were originally horizontal. does superposition mean? Let me turn this on and I'm going to give you 20 seconds here. No, 51, 55. Oh, man, you guys are looking right in. Okay. You didn't answer in 20 seconds. Slide is done. You missed your chance. That means not only did you miss your chance of getting it right or wrong and getting a point for that, but you just missed a chance of just answering. So you don't want to not answer a clicker question. At least you can get 1 point just for being here and trying. So give it a couple of seconds before the time runs out to make sure it gets registered and it gets recorded. Okay, don't wait till the last second. Let's see, how did we do? Well, looks like everybody, for the most part, kind of thinks B is the easiest. The youngest rocks are on top. That's right. Superposition. Super above, position in the stack. And how can I have the top of the stack if I haven't already built the bottom? It's like trying to build a house and put the foundation in last, right? You gotta have the bottom before you can build the top. And this is just a basic law, right along with original horizontality. Superposition are kind of some of the real basic, fundamental concepts of trying to figure out the stratigraphy. Okay, so you did a good job on that. I can even see cross-cutting relationships on places like the moon. Here you can kind of see this is a flow front for some lava. You can see a bunch of pock marks from some meteorite impacts. And I think you can see here that the lava flow on top is younger. That is coming over the lava down here. And everything then has been covered fairly equally with the meteorites. You don't see one peppered and the other not peppered. So it says, first we had the older lava flow, then we had a younger lava flow come in over it in the northern half of the picture, and then we had a meteor shower that pockmarked it all. So I can kind of figure this out. Even though I'm not there, and I'm looking at it through a telescope, I can still develop a sense of what events occurred up on the moon. So how about this one? This one really gets obvious. I've got this big impact, then I've got a second impact here. I've got all the debris that is the splash out of this bigger impact, and then some of the splash from the smaller impact. What about these guys? When did they occur? You don't really have a cross-cutting relationship other than they're cutting through the splash from the big impact, so you know they're after the big impact. That had to occur first, the big impact. So you know these are the second in order, but did these occur before or after this big impact? You can't tell. It doesn't appear to cut the splash from that, just because it's not close enough. So for these three guys, you kind of have to say, well, it's post the big one, but it could be before or after the second one. You don't know. Or it could be coincident with the second one. So sometimes you can kind of get a bracket on things, but you can't get it exact. Okay. It's often been said that there's probably more rock missing on Earth than there is present. The idea that rock can be eroded away, and the surface that's left is what we call an unconformity. If it's conformable, if it conforms, everything marches along just the way it should, layer by layer. But an unconformity says, uh-oh, there's a break in the succession. Something happened that there's a layer of rock missing. That's an unconformity. So it means not only is there a rock unit missing, but it also means that the time for that rock unit is missing also. The time is not represented there at that section. Now, what could cause that? Well, maybe the conditions at that particular location changed. Maybe there wasn't much rainfall for a few years, so the sediment wasn't being carried in and deposited there. In other words, the rock just wasn't formed ever. Or maybe it was formed. Maybe it was a nice thick unit, but then we had a period where there was a lot of erosion and that rock got worn away and stripped back out. Maybe even some of the rock layer beneath got stripped out. And then new deposition began again. So kind of the two big answers to that question are, one, it never got formed, or two, it was formed and then eroded back away. Okay, so let's kind of talk a little more about unconformities. We can identify three different kinds of unconformities, and we do that simply by looking at what's above this unconformable surface and what's below. The unconformable surface itself represents missing time. It's like the 18-minute gap in the Watergate tape, you know. Something happened there, but it's missing. You don't know. We can identify what we call an angular unconformity, a nonconformity, or a disconformity. And let's talk about each one of these in turn. An angular unconformity simply says, here's my surface, there's my gap in time, my gap in rock. I've got flat-lying sedimentary rock up here on top, in this case a limestone. Notice how we represent limestone with kind of this brick pattern? That's the traditional symbol of limestone. But below that, these rocks are various different lithologies, and they're all tilted up at an angle. And the erosional surface that represents the unconformity has eroded those units off, cutting across the ends of those units at an angle. So everything below is tipped at an angle, so we call it an angular unconformity. And that's got to be pretty easy to identify, don't you think? And you both angle stuff down here, flat stuff up there, you just draw a line right on the rock, no sweat. A nonconformity, well, let's do a disconformity. Disconformity is a little tougher to identify. Again, we have flat-lying rock up here. We've got some limestone. And notice we've got a flat-lying shale unit below it. And shale is just lithified, compressed, compacted, cemented muds and clays and silts. And it's turned that into a shale, a harder rock. And notice we use this kind of dashed pattern to denote shales. That's kind of a typical symbol we use there. And here's my erosional surface right here. There's the disconformity. And look at what's below it. It's not angular, older rock, but it is things like granite, igneous rock. Whole different kind of rock. And it's massive. You don't see bedding. You see rock that's been in place subterraneally all throughout the area. And you'll notice here we have got inclusions. Here's a chunk of the rock that's included now in the basal sediments that were first deposited on that eroded surface. So it's picking up some of the gravel and the debris of that eroded surface, incorporating that into the basal part of that unit, and we see these inclusions. So that helps us identify the fact that this was here first, this was all deposited later on. But there's a time gap in there. Not too hard to identify because the rock type is so different. And you'll notice the rock type up top is the same, but now we've got igneous or highly metamorphosed rock down below. A nonconformity is really pretty tough to identify because it's flat-lying sedimentary rock up on top and it's flat-lying sedimentary rock down below. And here's our erosional surface cutting along through here. Wow, it looks like it might just be the top of that one bed. and the next bed was conformably deposited right on top of that with no gap in time. So how am I going to pick up the fact that there's missing section there, that there's an unconformity? It's tough. Oftentimes in the field, you don't quite see that. But when you get the rock back to the lab and you look at the fossils, all of a sudden you go, ooh, these fossils are like Triassic fossils. And the Jurassic fossils are missing, and then the overlying stuff is Cretaceous fossils. And you kind of go, the fossils are telling me that. So that's where this becomes kind of an important aspect of paleobiology. So nonconformities are the hardest to figure out. Angular are the easiest, and disconformities are kind of the same. Okay, so here's an angular unconformity. You can see the time gap here at the erosional surface. Notice the inclusions. And we've got flat lying rock on top of it. And I think you can pretty easily pick out that unconformity. So I would look at kind of this type of scenario and how that might have formed. I would go, okay, we've got some deposition going on, laying down some rocks. Then this whole area had to kind of be uplifted and tilted. So there's probably a big mountain event going on nearby. And then I had to have some erosion that planed everything off. And then things had to change back to a basin setting where I could have more deposition again. So it kind of implies that you've got some uplift and then some subsidence in this process of creating this unconformity. So today, there's my angular unconformity. This is an angular unconformity over in Scotland. This is known as Sicker Point. And it's famous because this is where angular unconformities were kind of first figured out. And remember we talked about James Hutton, the guy that figured out uniformitarianism? This is part of what he figured it out with. He said, look, here I've got rocks going up and down. These are old igneous rocks. Here I've got sandstone, the old red sandstone sitting on top of it, coming across this. There's my angular unconformity right along there. He was the first to identify it. You go over to Scotland and see this today. It's really cool. It's right along the coast. And this was one of the things that he said, look, this didn't happen overnight. First you had to lay down igneous rocks, then you had to uplift them and tilt them, then you had to plane them off, then you had to deposit sandstone on top of it. That takes a lot of time. And he would point to this and say, there is no way you can do that in 6,000 years. And he was absolutely correct. Okay, a nonconformity. Here I've got older igneous or metamorphic rock. I've got my unconformity right here. Inclusions showing me that it's an erosional surface, and flat-lying sedimentary rock deposited on top of it. This is the Canadian Shield. The Canadian Shield are all Precambrian granites. Remember that old age, more than 560 million years ago? These are granites. Some of them go back into the billions of years. And as that was all eroded, those sediments were carried southward, lapped up onto those old Precambrian granite beaches, and all those sediments, those sands, those clays, those limestone, all of those formed as sedimentary rocks that kind of make up in from about the UP down, and it just laps up. The sedimentary rocks just kind of lap up onto this core of the continent, this Precambrian shield of granite. And this is the erosional surface where those granites were eroded, providing the sediments that were then relayed down on top of them, lapping on up as sedimentary rock. Pretty cool. You can see this transition right here in Michigan, up in the UP and the northern part of the state. So I kind of look at this kind of a scenario. I've got an area and I've got this big, giant intrusion of magma that's coming up from down below, but it doesn't make it to the surface. So we don't see a volcano, but it kind of, runs out of steam down at depth. We know that they've got to be at least about 7 kilometers below the surface. There's a lot of sediment still sitting there. And it cools off, forming this big granitic body. Then we have an erosional event, probably some uplift, and you'd expect some with all that intrusive material. And we have erosion. It cuts all of this 7 kilometers of overlying sedimentary rock away, exposing the top of this granitic batholith. Then, for some reason, subsidence, things cool off, shrink, subside. It becomes a basin again, and we start depositing limestones and shales. Again, an eroded surface, inclusions, just what we'd expect. And there we have our nonconformity. If you think about it, the present day surface that we're walking on is a big, giant unconformity. Right? If there's not deposition going on in the area, there's erosion. You very seldom get anything but either or. So you can look at it as being, for the most part, a big unconformity that you're walking on. Here you can see this nonconformity in the Grand Canyon. You've got all these high-grade granite gneisses, so they're probably both igneous and metamorphic origins. And you can see right there, there's your nonconformity. You can see all the flat-lying sedimentary rock sitting on top of it. Look, just jumps right out at you. And here we see a disconformity. There's our erosional surface. Oh man, that's pretty hard to tell, isn't it? Everything's flat-lying top and bottom. But here, I've got brachiopods in the top that date back to 290 million, but the brachiopods just below the unconformity go all the way back to 490 million. I've got a gap of about 200 million years represented by this disconformity. So it took some fossil work to nail down the age. So I'd see something like this. Deposition, uplift and erosion, deposition again, and in both cases, flat-lying sedimentary rock above and below the disconformity. And this is what we see in the Grand Canyon. This is what John Wesley Powell was able to figure out. This was what was so shattering in geology when he made that trip in 1869. Here's the Grand Canyon down here. And the first thing in the inner gorge is you see the Visnu schist. It's a metamorphic, highly igneous, highly metamorphosed rock. Above that, you see this unconformity here that's an angular unconformity. Flat-lying sedimentary rock sitting on top of angular stuff. But look at back over here. We've got this granitic intrusion that happened before this nonconformity here, because it cuts the end off the granite. And then this angular unconformity cuts through this. So this was intruded into this basement rock. Then this was eroded. Then it was all tipped and tilted. And then this cut through everything, first forming a nonconformity here between the granite and the sedimentary rock, and then an angular unconformity here. And later on up there, a couple more unconformities, and in this case, flat-lying sedimentary rock, both above and below, so those are disconformities. So we kind of saw it all right here in the Grand Canyon. And all of a sudden, all these theoretical concepts of stratigraphy, you could go, oh, it's right there. It's happening. Okay, so here's a clicker question. Trust me, it says igneous granite overlaid by flat-lying sedimentary rock would indicate what type of an unconformity. A would be a nonconformity, B, angular unconformity, C, a disconformity, or E, none of the above. Take 20 seconds. Okay, give me an extra second. And the class says, that pretty much covers them all, doesn't it? Okay. Well, remember the key here was the idea that they all have flatline symmetry rock up above, right? But here the key was it's the granite igneous rock down below. So that makes it a non-conformity, just like Canadian sheet. Okay, so kind of keep those different types of unconformities in mind. And at this point, I'll break the lecture. We'll pick it up from here next time.